Hello, this is David with Everything Economics. And today, to continue our exploration of critical reasoning, we are going to be talking about scientific reasoning. And this is a lecture that is in three parts. And so this is the first part. And the second and third part will probably come in another day or two. But so for now, scientific reasoning, part one. All right, so what's the outcomes for today? Well, students will have a basic understanding of a scientific approach to research. This is extremely useful when you're in college. You'll distinguish between rational and irrational beliefs, distinguish between science and superstition, and understand Occam's razor as a philosophical tool. All right, first of all, the natural sciences. Natural sciences consist of things like biology, chemistry, physics, astronomy, and then the earth sciences such as geology, oceanography, and climatology, etc. Mathematics is not a natural science. It is a tool for measurement. So uh, mathematics is a tool, it's not an actual science. And then engineering is not a natural science as it's focused on creating and controlling technology. So those two things are not considered natural sciences. Okay, now when doing scientific studies, there's four basic guidelines. Number one, it requires using the scientific method to justify claims. And we'll talk about the scientific method here in a few minutes, but you probably learned a little bit about the scientific method back in maybe your high school science classes. Um, and we'll go into a little more detail in a couple of more slides. Another guideline is that two, science assumes a background of no miracles and no supernatural causes. So in science, everything can be explained through some kind of logical reasoning. There's no magic, no miracles. And so this is a lot of times where religion and science have conflicts because in religion you might have beliefs or miracles or some trying to explain things that you cannot fully explain maybe through science. But science says there's no miracles, there's no magic. There's everything has a reason, or everything is caused by something that can be explained. Number three, science continually makes inferences for new predictions in order to test general theories about how the world works. What this is basically saying is that science is continually to evolve. In other words, what is true today may not be true in the future as new discoveries are made, new ways of doing things, new observations, and so forth. So science is not it's not unchanging. It continues to develop and change over time. And I'm going to give you one little basic example of how science can change. So let's say, for example, gravity. We all know what gravity is, but the scientific theories behind gravity have changed over time. So, for example, what is gravity? Well, if you were in ancient Greece a long time ago, uh, you would say that gravity is controlled by four elements. And this would be, let's see, air, fire, water, and earth. And the basic idea is that earth is heavy, therefore it wants to go downwards. Water is heavier, is not heavier, but is also heavy, and it also wants to go down as well. But earth, which is your dirt, is stronger. Fire rises, so therefore fire is lighter, And of course, air is lighter because air rises even above fire. And so that was their understanding of how gravity worked. It worked based on these four elements. Well, fast forward long time, and we have Isaac Newton, who comes up with his idea of gravity, with the laws of gravity. And he comes up with the laws of gravity and the main one is that mass attracts mass. And so that was his idea of gravity. And then fast forward a little bit further, we have Einstein. And Einstein says in his theory of general relativity that gravity can bend light. Let's see, write this here. General theory of relativity. That gravity is strong enough to bend light. And that's pretty much where we are right now. Now, in the future, we may come up with some new theory or some new idea about gravity. But basically, science is continuing to evolve, continues to get modified and change over time as new discoveries are made. All right, and number 4, scientific claims are to be true or false depending on the evidence. So, for example, if you have a theory that couldn't be shown to be incorrect, no matter what happens, then you aren't doing science. So, in other words, when you're doing science, you have to be able to either prove something is true or prove that it is false. You cannot, if you are unable to prove anything, then that would not be considered science. And an example would be Sigmund Freud. He has a lot of theories about child psychology and about how, as a child, as an infant, you might experience trauma as a young baby or as a child, and you can't actually prove it. There's no way to prove it, and there's no way to disprove it. So it's kind of like, well, you can't. There's nothing you can do about it. Another example currently would be string theory, which is kind of another theory in physics to do with a little bit to do with gravity. Of course, this is not a science class, but the point being is that currently there's a string theory, and you can go look on the internet to find out what it is, but there is no way to test it to see if it's true or not at this time. Now, maybe in the future, things might change, but right now, you can't test it. So there's no way to prove it or disprove it. All right, so these are basic 4 guidelines when dealing with scientific study. Now, let's go into an example here. Let's test some knowledge. Given the information already mentioned, the profession of a biologist is most like that of a butterfly collector, B, nuclear engineer, C, astronomer, D, heart surgeon, or E, inventor of new lighting systems. Now, you can pause the video and just figure out which one you think a biologist would be closest to. And let's see, let's go ahead and go through this. A biologist, we know, is a scientist. And we do know that letter E, inventor of new lighting systems, that's not a scientist. So we do know that that's not going to be the answer. A heart surgeon, well, a heart surgeon is a medical doctor, and yes, they do require knowledge of biology, but they're more trained in actually correcting something or changing something, or performing surgery on the heart. And so that's a little bit different from what a biologist would be doing. So we could cross that one out as well. An astronomer is someone who studies the stars, studies space. He does measurements. They gather data, they gather information, and try to come up with a theory or an idea, or to discover how things work, like how the sun works and how the stars light up and so forth. That may be possible. Nuclear engineer, again, engineer, as we discussed earlier, is not actually a science. So as an engineer is one that tries to control or develop technology uh, to control something or to create something, and so that would not be it. A butterfly collector, yes, certainly. If you like butterflies, you might be a biologist, but anybody can collect butterflies. It does not have to be a biologist to do that, so that would be incorrect. So we are left with astronomer, and yes, both of them are scientists, and both of them study their respective fields. Both of them take measurements, or they gather data, or they gather information. They try to learn more about their particular field. And so in this case, a biologist and astronomer would both be similar because they are both scientists. All right, let's go through some basic terminology. For science, a test is an observation or an experiment intended to provide evidence about a claim. So you claim something and you want to test it to see if that is true or not. And the test can be an observation, and the observation could be just whether you visually see it or whether it appears in data. A law of science is a sufficiently well-tested general claim. So an example would be the law of gravity. Mass attracts mass. It's been tested over and over again. It works. And so it's basically a law of science. A theory is proposed explanation or comprehensive integrated system of laws that could be used in explaining a wide variety of phenomena. So, for example, a theory of evolution. Theory of evolution is the idea that all life evolve or develop or change over time. And so this is it covers a wide area, not just animal life, but human life and plant life and so forth. And so you have the theory of evolution. All right. Testability is a key ingredient of any truly scientific claim. So as we said earlier, as long as you can test it, if you can test to see if it's true or false, it has to be testable. If a proposed hypothesis, which is a claim, cannot be tested even indirectly, then it is not scientific. For example, the current laws of chemistry will hold true only as long as the devil continues to support them. After all, the devil made the laws and he can change them on a whim. Luckily, he doesn't change his mind too often. Obviously, in this example, it is using the devil or a supernatural entity that can create laws or change laws at will. And that is obviously not scientific at all. So, all right, now we're going to go into the scientific method, which is a method of discovering possible causes and then testing them. The key idea in justifying a claim about what causes what is to actively test alternative causal stories, hypotheses, in an attempt to rule them out. Testing is active, whereas observation alone is more passive. Okay, so let's go to the next slide and go over scientific method. All right, so first of all, we start off making observations. So we make observations. What do I see in nature? Or this can be from one's own experiences, thoughts, or reading. You make an observation, and then you go on to your next point, which is to think of an interesting question. Why does this pattern occur? How does this occur? What causes it? And so forth. And then after you think of a question, you form a hypothesis, which is a general cause of the phenomena that you are wondering about. After that, you develop a testable prediction. You develop ways that you could test this hypothesis to see if it's true or not. Then you gather more data to continue to test the predictions. So relevant data can come from the literature, new observations, or formal experiences. Thorough testing requires replication to verify the results. And this is key, replication of the results. If you keep testing and testing something and coming up with different results, then something is very wrong. But if you keep testing and testing and you're getting similar results, then you may be onto something. There may be you might be finding a pattern or some kind of cause for something. And of course, this is going to be basically you're going to be going in circles, refining, alter, expand, reject hypotheses, develop, maybe test again, gather more data, refine, alter, expand, and so forth. You might go through this several times. And then you go into developing your general theory. So your general idea. So it must be consistent with most or all of available data and with other current theories. So that's basically the scientific method. All right, and so here we have an example. Just another, we have an observation, we observe, then we ask the question why, and then we come up with a testable explanation, a hypothesis. So for example, salt water has a lower freezing point than fresh water. Or we could say that a spirit makes the fresh water freeze faster. Now, obviously, salt water has a lower freezing point than fresh water. This is something you could test. So you could actually test that. You could use a thermometer and test when fresh water freezes and when salt water freezes. If we just say a spirit makes the fresh water freeze, well, that is not scientific and that's not logical or not something that we would appeal to. Then you develop a testable prediction. You create an experiment where you predict the outcome, and hopefully, if the experiment goes well, then that is the outcome that you would get. And so in this case, the prediction would be fresh water freezes at 0 degrees Celsius, but salt water doesn't. And then you test it. And then you refine, alter, modify if you get different results of your testing. All right, that's it for this part of the lecture. So this is part 1 of 3. So stay tuned for the second one and then the third part.